river protections, like, for instance, levees or embankments. Embankments are walls that are built on the sides of the river to prevent erosion. For this kind of protections, you may just need the peak flow or peak river stage. In some cases, we assume that the knowledge of the peak flow is enough, because it's much easier to estimate, as I said, a single number than the whole hydrograph. Of course, the reason for preferring, because if you give the whole hydrograph, one may say, but why do you limit your attention to the peak flow? Let's estimate the whole hydrograph, which includes the peak flow. But the reason why we limit our attention to the peak flow is that it's easier to estimate. And of course, as engineers, we have to look at the best solution, and sometimes simplicity is an added value for finding the best solution. Sometimes simplicity is needed for many reasons. And therefore, in some cases, we limit our attention to the peak river flow. And today, I will speak about estimation of the peak river flow, not the whole hydrograph. And then later on, I will mention to you briefly methods for estimating the whole hydrograph. So, in order to move forward, now we have identified the design variable. Do you remember the scheme that I showed you before? We are at this stage. We are here. We started from the solution, namely we need levees, we need bridges, we need dams, and then we got here design variables. And then I said, okay, it may be the flood hydrograph, it may be the peak flow. Now let's go back to the models, which is the interesting part for us. But first of all, let me give to you some definitions. I'm sure that you already know them, but I prefer to remind you. And you know, definitions are sometimes boring, but they are necessary because we need to know what we are talking about. So if I say a river, I need to make sure that you know what is a river, and this is trivial. But if I say river flow, I need to be sure that you know what is it. Because I am sure that if I made a survey now, some of you cannot define the river flow. Maybe that you have an intuition of what it is, but probably, even if I asked you the units in which the river flow is measured, I'm not sure that you know them. The definition serves to this purpose, to clarifying what we are talking about, which is essential if we want to talk about models. Okay? So basically, we are, as I said, referring to rivers, and I have a link here to another Wikipedia page, and let me see. Okay. Let me find it. River. Okay, so this is, as I said, quite trivial, and basically here the river is a natural flowing water course, usually fresh water, flowing towards an ocean, sea, or lake. Now, it's a water course, so it's a course of water. Here it says naturally flowing. I would remove naturally, because there are no natural river where we live. There are natural rivers in the world, of course, but where humans live, there are no natural rivers. And the rivers we are interested in are no natural. And the explanation is very simple. If we are designing an infrastructure, the river is not natural. Okay? Or with the only one exception in which you are the first one designing an infrastructure on that river, which is very difficult that it may happen to you. Okay? It's very unlikely. Usually, a river is not flowing naturally. So it's not enough that we learn how nature makes the river flowing. We need to know what are the mechanisms relating humans and the river. As I said last week, we have to stop referring to pristine environments. Modern hydrology needs to refer to human-impacted environments, which is even more interesting. And don't make the mistake to consider that natural environments are necessarily nicer than human-impacted environment. This is not true. In some cases, the natural environment is very hostile. The reason why humans make infrastructures, make buildings, is to make the environment more receptive, more friendly. Usually the human-impacted environment is much more friendly than the natural environment. And it's also interesting. So, and of course sometimes humans make mistakes, and so they make the environment really bad, really impacted in a negative way. And this is what we want to avoid. We study engineering because we want to make sure that our development is sustainable. We need to make structures, but we also need to make sure that every intervention is sustainable. So this is the river, and this is quite trivial, as I said. Now let me turn to the definition of river cross-section, because you know it is written here. The estimation of the peak river flow, like the estimation of any design variables, needs some specifications. So if you want to estimate, for instance, the design variable to design a roof, you need to know what is the expected snow height that may fall over the roof. So you need some specification. And for the case of the peak river flow, you need to specify these three quantities. Three main specifications: the return period, the river cross-section, which in turn refers to its contributing catchment. Now, let me start with these definitions then. What is the return period? Basically, there is also a link to a Wikipedia page here. The return period defines how much a peak flow is extreme. So we speak about peak flow, but of course there may be many peaks. There are floods that occur on average once in a year and have a peak flow. And there are floods which may occur on average every 1,000 years, so very unlikely to occur. And of course, these floods are much more impacting, are much more extreme. So we need to quantify, I used here a term which is not correct, extremeness. We need to quantify extremeness. Why do we need to quantify it? Because when we design a structure, it is quite intuitive that we have to make a prediction of the expected lifetime, and therefore we have to make a prediction of how much extreme should be the event to which the structure is expected to resist, to survive. So basically we may say, okay, I'm not much concerned if a bridge is overtopped by water. I'm not concerned because I may put like a stoplight which stops people when there is a risk of flood. And then if there is the flood, I tolerate that the bridge is overtopped. So basically I designed the bridge to resist against a not really extreme peak flow. On the other hand, I may have a bridge that is a bridge for a highway. I really want to make sure that it's not overtopped, even if a big flood occurs. And therefore it means that the design flood should be extreme. And a way to quantify extremeness is to quantify then the frequency of occurrence of the event my infrastructure should be resistant against. You can understand that if I say that a flood occurs on average once a year, then as I said, the peak flow is of course, extreme. But if I talk about a flood that occurs in average once in a 10 years, it means that the related peak flow is much higher. So basically, the return period, a definition which I already used because I said a flood that occurs on average once a year, once every 10 years, once every 1,000. I am quantifying, you understand, a return period. So what is the definition of a return period? It's written here. The return period for the case of the peak river flow is the average time interval separating two occurrences of equal or higher river flow with respect to an assigned value. So basically, let me make an example which is written there. For the Po River at the closure, at the last part of the river, we know that a river flow of about 13,000 cubic meters per second occurs or higher. So I say again, we know that for the Po River, at the end of the river, a river flow of about 13,000 cubic meters per second or higher occurs on average every 50 years. It means that the return period for a river flow of 13,000 cubic meters per second in the Po River at the closure, at the final reach, is 50 years. So I fix the river flow, a river flow value, and I estimate its return period. Or I may take the other way around. I fix the return period, and then I estimate the corresponding peak flow. This definition of return period, I may ask it at the exam. And what you don't have to forget is to say average time or expected time, which has the same meaning, but let's say average. Why is that? Because you don't have to get the feeling that if I say that the return period is 50 years, once a flood occurs, you are safe for 50 years. This is not true. And this is what the public usually understands. So if you go to, if you speak with the man on the street and say the flood that occurred yesterday in the Po River has a return period of 20 years, she understands that for 20 years she is safe. This is not true. It may occur tomorrow, the other flood, because it's the average time. For instance, look at the Po River. I said 13,000 cubic meters per second. A similar flood occurred in 1951, in 1994, in 2000, and that's it. In the recent past, in the past 100 years. So it means that 50 years passed from 1951 to 1994, but then only 6 years between two occurrences of a similar flood, equal or higher. And then in the past 16 years, nothing occurred so far. So it's the average time. Let's read again. The average time interval separating two occurrences of equal or higher river flow with respect to an assigned value. And here there is the example of the Po River. So what is, to give you an example, what is a very easy way to estimate the return period of a flood? So let's suppose that you have 10 years of observations or river flow measurements. Let's say taken every day. We call it daily river flow observations. And you have 10 years, so you pick up the highest value. So this is a value that occurred once in 10 years. So you may say, let me say that the return period is about 10 years. And the second value then, provided it is independent. Independent means related to another flood. Because of course, if you have one flood, you may have a daily river flow observation here, but another observation daily here, maybe. So these are dependent. It's the same flood with two observations. So in order to get the second one event, you have to refer to another flood. So you have to make sure that the second number if you rank the numbers from the highest to the lowest, you have to make sure that the second number is independent. And therefore, the second flood has a return period of 5 years, more or less. The third flood has a return period of 3.33 years, and so on. And indeed, if you look at the Wikipedia page of the return period, there is, they propose a formula for which it's an analytical representation of what I just said. Here is the formula. And n is the number of years in the record, and m is the number of recorded occurrences. So this is what I just said. I said the largest one, the number of occurrences is 1, and therefore the n is 10 years, and I said 10 divided by, let's forget about the plus 1 for now. 10 divided by 1 is 10. The second one, m equal to 2, the return period is 5. The third one, m equal to 3, the return period is 3.33, etc. Let's forget about the plus 1. Okay? This is a very intuitive way, if you have data, to compute the return period for an assigned river flow value. But there is a but. You may say, but 10 years are enough. I mean, if I take other 10 years of observations, I get a different estimate. Because of course, observations are just a representation of a single occurrence lasting 10 years in this case. So we have to be careful, because this method for estimating the return period is reliable if you have a lot of data, a lot. So if you have 1,000 years of measurements, of course it's very reliable. If you get the highest value is based on 1,000 years of observations. The problem is that we don't have 1,000 years of observation. In hydrology we have, as I said, about 100 years. And but if you have like 5 years, really, it's not representative. So be careful when you estimate the return period you need, and it is written in my notes. You need a lot of data. There is uncertainty in this estimation method. The model that we are using here, because this is already a model, it's a model using the data. In the classical hydrology, they call it data-based model. The model is affected by uncertainty. And therefore, this is the reason why a plus 1 is added here. Adding a plus 1 is a way for taking uncertainty into account. It's like a safety factor. And you see that the plus 1 is almost unimpacting if n is large. If n is reduced, the plus 1 is a safety factor that is impacting. Think of if you had only one data, it means one occurrence. You would take the data and you would assign to it a return period of 1 year, which is not a prudent assumption. You need to put a safety factor there. I understand that it's not immediate to you the reason why it is a safety factor, the plus 1. Let me postpone this discussion. And if you make this computation, you would realize in practice, you take a sequence of numbers, observed or simulated, and you make this computation of the return interval, or return period and the recurrence interval are synonyms. Basically, if you make this computation in practice, you would realize that a value that is close to the average has a return period of about 2 years. A value that is close to the average has a return period of about 2 years. This is easy to check. if you make just a simulation or you take some numbers, it's easy to check. So basically we need this specification of the return period, which is basically the lifetime of the structure. So if we design a dam, we also have some indications which are given to us on the expected lifetime. But it's not just a matter of lifetime, it's also a matter of the risk that is induced by the collapse, the possible collapse of a structure. So if you are not concerned by the collapse of a structure, collapse means that the structure doesn't deliver the function that is expected to deliver, not necessarily is destroyed. So if you have a collapse and the collapse is not concerning you, you can take a low return period for design. For the case of a dam, you are much concerned by a collapse. And therefore, usually dams are designed with a return period of 1,000 years or 500 years. Instead, the urban drainage systems, they are designed with a return period of about 2, 5, 10 years. Because usually you are not concerned by the collapse or the failure of a urban drainage system. At least you get the roads with some water flowing over them, but it's not a danger for the life of the people. But if you instead have some, I don't know how to say in English, but the places where you put the cars, the rooms where you put the cars, we say in Italian autorimessa or garage, and these are underground, you may be concerned by the failure of a urban drainage system because people may get drowned while they try to get the car back. And therefore, in this case, the law suggests you to use a higher return period. The return period is normally suggested by law. So this is a specification that is quite easy for you to obtain. It's normally suggested by law. And there is here a link which I found quite nice. It's not a Wikipedia link. And this page is titled On the Return Period to be Used for Design. Victor Miguel Pons is a very famous professor working in the United States now, and he delivered important contribution on open channel flow. And he makes some examples here. And basically, why does urban drainage use short return periods? This is why the reason I already mentioned to you. And what is the return period for regional flood protection works? 50 or 100 years. I confirm this estimate. Usually, when we talk about river levees, they are designed for a return period varying from 50 to 200 years, depending on the vulnerability of the flood-prone areas. And then highway design and bridge design. Bridges in Italy, there is usually, you need to design them for roads of national importance. You need to design them against a return period of about 200 years. So the return period is usually specified by law, and if it's not usually specified, if it's not specified by law, you can find references in the literature like this one. So the return period is something that we should be comfortable about at this stage. And then let me define the river cross-section. The river flow refers to a river cross-section. And what is a river cross-section? It's important to give the definition. So basically, the river is a water course, as we saw. If you cut the water course with a plane that is perpendicular to the velocity vector in this site, you get a geometric figure like this one, which is called the river cross-section. I'll say again, because this is important, I may ask you this question. If you cut the water course or the river flow with a plane that is perpendicular to the velocity vector in that side, you get the river cross-section. Basically, you get a site assigned because you have to build an infrastructure there. Then you go there, you are close to the river, you take a plane and you cut the river by keeping the plane perpendicular to the velocity vector. And then you get this kind of geometric figure. In fact, the cross-section defines the river geometry. When you talk about or you read about river geometry, cross-sections, and of course they are spatially varying, and therefore you need many of them to define the river geometry, and they are also, unfortunately, I would say, varying in time. So in order to get this geometric figure, you need the help of a surveyor, and she has to make a survey. But then, after some time, the geometry is changed. So when you get a river cross-section, which is usually given to you, you are the engineer, you have some people, either you call the surveyor to make the survey, but in most of the cases you will have some people giving the river cross-section, giving the river geometry to you. The first question that you should ask is, what is the date of the survey? Because if they tell you 50 years ago, useless. Unless it is an artificial channel made of concrete. But in this case, this is clearly a river, and if it is subjected to erosion, it is subjected to human impact. So basically, the geometry changes in space and time. The geometry may not change in space, and this only happens for artificial channels. So we say that the channel is prismatic, which means that, again, the geometry doesn't change in space. So when you listen about a prismatic channel, you know what it means. You know that one survey of the river cross-section is enough to define the channel geometry. In most of the cases, you will deal with non-prismatic channels, and therefore you will need a lot of cross-section. And your question may be, how many? So there is a rule of thumb for big rivers. Big rivers are also less spatially varying. You can understand that. If you look at the Danube River, you see that the geometry doesn't change in a short spatial step. If you look at a mountain river, you see big changes. Even if you move about, you may see a cascade. You move 3 meters and the geometry is completely changed. So a rule of thumb says that for big rivers, we need one section every 200 meters to get a reliable definition of the geometry. Now, there is one thing that you may ask me. I said perpendicular to the velocity vector, and you may ask me, but where I should take the velocity vector? Because if I move in the river cross-section, of course the velocity vector may change. But some of you took subjects of open channel flow, so some of you already know what I'm saying. If we take the assumption of gradually varying flow, the velocity vector doesn't change in the cross-river section, in the river cross-section. Again, if we take the assumption of gradually varying flow, which is usually taken in river engineering, not always, but usually it is, the velocity vector doesn't change across the river cross-section. Okay, so the river cross-section is defined. And then, what is the definition of river flow? A synonym is river discharge. the river flow is defined for a given river cross-section. So before talking about river flow, you need to identify the river and the river cross-section. So when we talk about a river flow, we always need to say the river flow of the Po River at Ponte Lago Scuro, a location along the river. The location where you draw the river cross-section. Keep in mind that the last cross-section of a river is also called the closure of the river. The closure is the last river cross-section, which is usually placed by assumption. For instance, the closure of the Po River is at Ponte Lago Scuro, which is a location where the last gauge, flow gauge, is located. Then the river continues, but by definition we take Ponte Lago Scuro as the closure of the Po River. So basically, what is the river flow across a cross-section? It is the rate of volume of water passing through the river cross-section. The rate of water volume passing through the river cross-section. What is the rate? Is a measurement per unit time. So you may also say it's the amount of water volume per unit time, which is equivalent to, say, the rate. So you may say it's the amount of water volume per unit time passing through the river cross-section. This is the river flow. As I said, it is intuitive, but you need to know how to define it with certainty. So please learn it. I may ask this question, give me a definition of river flow. It's a very simple question. Simple answer, but of course it's simple provided you know it. And the river flow, by adopting this definition, is expressed in terms of units as a volume over time, and usually it's expressed in cubic meters per second, or this is usually for big rivers. For small rivers, it's expressed usually in liter per second. But this should be really very small, like the flow that you get when you open your tap usually is measured in liters per second. And you should never forget that 1 cubic meters per second is equivalent to 1,000 liters per second. When I got my degree in civil engineering, I didn't know that. So I always tell students, don't forget, because this is one of the things that if you make a mistake about, when you speak with the technicians, you are lost. So if you speak with, I don't know how to call it in English, the craftsman that makes repairs to the taps, we call it Hydrology in Italy. So if you speak with such a person that probably doesn't have a degree, and you show that you are an engineer and you don't know how many liters are included in a cubic meter, you are lost. You should better stop talking with that guy. He will not listen to you anymore. So this is something that we have to be very careful about. Like when I started, I did some professional activity before entering in the academia, and I made some of these mistakes. So I realized that really it's something that, it's better to avoid. Okay, so basically we have defined the river flow, and now let me define the catchment, or the contributing catchment. And there is a Wikipedia link, but I don't really like the definition that they provide. I prefer that you stick on this, and which are more or less equivalent, but I think, it's better that there are some more specification in my definition. The contributing catchment is also called the catchment, with the implicit term contributing. It's also called river basin. It's also called watershed. Drainage basin also. So they are synonyms. So in the English literature, they use the term watershed. In the American literature, they use the term catchment, or the other way around, I don't remember, but I think the English, the UK should be watershed. And then some people use drainage basin, the geologists usually say drainage basin, or in a colloquial form, people say river basin. But what is then the catchment or watershed or drainage basin or river basin? It's a portion of geographical surface, and basically it's the entire portion and the only portion of geographical surface that contributes to the river flow in a given cross section. I say again, it's the entire portion and the only portion of geographical surface that contributes to the river flow in a given river cross section. And the only portion is my addition, because the definition in Wikipedia says the entire portion of geographical surface. I prefer to say the entire and the only one, because you don't have to get any exceedance. And it is extremely important because, you know, if a catchment is extended, much extended, you would expect that the river flow is much higher, provided the rain is more or less the same. If a